All right, lesson 3-2 is over connecting representations of functions. So being able to look at a function in an equation, tables, graphs. So for Objective, be able to identify functions by their equations, tables, graphs. We're also going to look at nonlinear functions to kind of see what those look like and just identify some features of functions when you're looking at them in an equation, table, and graph. So for example 1, represent a linear function with an equation and a graph. So at a 10,000 gallon swimming pool needs to be emptied. Exactly 2,000 gallons have already been pumped out of the pool and into the tanker. How can you determine how long it will take to pump out all of the water into the tanker? So one way is to use the information given to write an equation. So functions are exactly what we did back with linear relationships. The only thing with functions is you can have nonlinear. So a linear relationship that we did last chapter were all examples of functions. So you're going to see a lot of the same vocab terms and the same strategies when we're describing functions as when we did linear relationships. So it's a nice blend there. So one way is to write an equation. So if you remember when we wrote equations, it was in the y equals mx plus b form. We're going to do the same exact thing for this. So the amount of water that was already pumped out of the pool was 2,000 gallons. Okay, 2,000 gallons have already been pumped out. This is going to be our y-intercept, or we call it with functions the initial value. Okay, it's the starting amount. So we started with 2,000 gallons being pumped out. The amount of water pumped every hour, so it gave us that information too. Did it give us that information? Oh, you know what? It was in the picture. The picture wasn't copied. So in the picture from the book, it says that it's taking out 720 gallons per hour. So I apologize for not having the picture in there, but this is 720. They had it in the picture that wasn't on your notes. So this is considered your slope because it's happening every hour. It's a constant rate of change, or you guys know it as slope. It's what's happening over time, the same thing. So this was our starting amount that was pumped out. This is how much is being pumped every hour. So when I want to put this into equation, you remember the form is y equals mx plus b. Your initial value or your y-intercept was your b, and your slope was your m. So when we plug in these values, my equation would be y equals 720x plus 2,000. Okay, so if I wanted to know how long it was going to take to pump that out, I could plug in 10,000 for my y because that's how much water is in the pool, and see how many hours it's going to take to get those 10,000 out. So if I go ahead and solve this, I would subtract 2,000 from both sides, and I would get 8,000 equals 720x. And if I divide 8,000, sorry, I ran out of room, but if I divide 8,000 by 720, you're going to get around 11.1. So it's going to take over 11 hours to get all of the 10,000 gallons pumped out of the pool. Another way that you can do this is to graph the information using your initial value and your rate of change. So again, on here, it was starting at 2,000. That's how much already has been pumped at 0 hours. And then every hour, we're doing 720 more. So when I go to graph this, I would be going up 720 every hour. So it's not going to be perfect on here. It's going to be hard to kind of estimate. But this is going to be going up every hour, up 720, so a little less than 1,000 on here. And you'll notice that if I continue this trend, that somewhere around 11 hours, I get to 10,000. So again, this isn't a perfect graph and it's not as accurate, but another way, if you're just trying to get a basic idea of how long it's going to take, is to make a graph and see how long it would take to get to 10,000. Okay? But the main point of this problem, I wanted you to understand, initial value is the same as our y-intercept, and the rate of change is the same as our slope. Okay? We move into looking at nonlinear functions, so representing a nonlinear function with a graph. So how can you determine whether the relationship between side length and area is a function? So we're going to create a table that relates the side lengths and the areas. So we're looking at a square. I can look at different side lengths, so maybe start at 0, go all the way to 5, just to get multiple data points here. So if I have a square that has a side length of 0, if you remember for area, you square the side because it's length times width, or side times side. So I would be doing 0 times 0, which is 0. For the area of a 1 by 1 square, it would be 1 times 1, which is 1. For the area of a 2 by 2 square, it would be 4, 9, 16, and 25. So basically just squaring each side length. Okay? Once you have all of your data points, you can go ahead and plot them on a point to see if they create a function and see what that looks like. So for this, 0, 0 was my first one. Then I had 1, 1, 2, 4, 3, 9, 4, 16. And you'll notice that this kind of is creating a curve, which we haven't, this is going to be hard to do with my little tablet here, but you'll notice that, and 5 and 25. You'll notice that my graph is curving. So unlike all of the graphs that we did last chapter, this one has a slight curve to it. Looking at our table of values up here, each of our inputs, our x values, had only one output that went with it, and because of that, it's a function. But because it curves like this, it's not in a straight line. There's no slope or anything like that. We say that this is a non-linear function. So the question was, how can you determine whether it is a function? Again, looking at each input has its own output. And again, looking at the shape of this graph, this represents a non-linear function. So we have a non-linear function. Okay, so the reasons why: each input has only one output. And it's nonlinear because it's not a straight line. All right. Example 3. Determine whether each graph represents a function. So you're looking at, does each input have only one output, or does each x value have only one y value? So for this, something that we use is called the vertical line test. And what that means is if I were to draw, it's hard to do, but if I were to take a ruler and I were to draw vertical lines, so up and down lines, on my graph at every point along this graph, it would only have one point at each of those lines, because each x value could only have one y value. So at x equals 2, y equals negative 2. At x equals 0, y equals negative 2. So you'll notice that each x value only has one point that goes with it. So looking along this graph, each x value here only has one y value for the whole graph. So for this first one, this is a function. So yes, or I'm just going to put function. So function because each x value has only one y value. Okay, let's look at the second one. All right, both of these are nonlinear functions. Looking at this one, I'm looking at, does each x value have only one y value that goes with it? As I move along this graph, you'll notice that yes, each x value has only one point, one y value that's going with it. So this one is also a function for the same exact reasons. Now this one, again, nonlinear relation happening here. If I go to an x value, so let's say x negative 3, you'll notice that at negative 3, there are two y values that go with that x value of negative 3. These two. If I look at 0, I have this point right here, but I also have this point here. So I have two different outputs for the same input, or two different y values for the same x value. If I were to do the vertical line test, you'll notice that it fails because it has more than one point basically on this function or on this relation. So I know a lot of people like to use the vertical line test just because it makes it a little easier to visually see, but you're looking at, does each x value have its own y value? For this one, it's not a function. Okay, and the reason why is each x value does not have only one y value. Okay, so that's how you can look at a graph and determine if it's a function.